All right, we're going to skip 2.4 this year. We're going to go to 2.5, and it's going to be covering continuity. Definition of continuity is going to be whether or not the limit of a function as x approaches a is equal to f of a. And that's going to tell me if it's continuous at a number a. Now, this looks pretty simple, but there's actually three things that's going on here. Okay? And so the very first thing I want to talk about is going to be the limit. The limit as x approaches a of f of x. This limit has to exist. It has to approach a unique number. It can't oscillate wildly. All that stuff we've been talking about with limits has to happen. Next, f of a right here. F of a has to be defined. It can't be a whole. It can't be an infinity there or a vertical asymptote. And the third thing that has to happen in order for a function to be continuous at a number a is that the limit and the function value have to equal each other. Okay? So if those three things happen, we say that it is continuous at a number a. If it's not continuous, we simply say it's discontinuous. Okay? And we'll see some examples of things that are discontinuous. So here we have a graph. I want to find out where my discontinuities are. And I'm going to state why. My reason why is going to be one of my three options that I just said. It's either going to be the limit does not exist, f of a is not defined, or they're not equal. The limit and the function is not equal. All right, so first one I see right here is at 1. Okay, I'm just kind of using a little Mario right here, and he's having to jump over a point. Anywhere Mario's going to have to jump on this line means it's not going to be continuous. Excuse me, I'm still fighting some of this drainage stuff that I was dealing with last week. So, our very first discontinuity is going to be at this 1 number, at a equals 1. Okay, and the reason is because there's a break right there. All right, but using my reasons from the last slide is that f of 2 is not defined. As you can see, I'm sorry. I'm wondering where's that 2 coming from. F of 1 is not defined. All right, there's a little hole right there where he just had to jump over. The left-hand limit and the right-hand limit look good. They're both coming into this unique number right here. But there is no f of 1. The next one, as we continue our little journey, looks like there's going to be a break right there at 3. All right, the break at 3, well, let's see. I got my right-hand limit coming in high up here, my left-hand limit coming in low. That limit does not exist. The limit as x approaches 3 of whatever this function is does not exist because the left-hand limit and the right-hand limit are not equal. All right, finally, it looks like something weird's happening at 5. See what's happening at 5. My limit looks good. I'm coming in the left hand and the right hand side the same. My f of 5, it's defined right here, but as you can see, my f of 5 is way up here, and my limit is way down here, meaning that they are not equal. So the limit as x approaches 5, while it does exist, and while my f of 5 exists, we simply are not equal. Did not come on the same page on that. So I like that. I like when they give me a graph of it. I think that's a good visual representation as to what's going on at certain discontinuities. Okay? But what if they don't give me a picture? We got several of them on here, don't we? All right. Well, let's work these out individually underneath. All right. Let's look at A. Right. Let's look at A first. It wants to know where these are discontinuous. So on part A, we have a rational function here. What could make something discontinuous on a rational function? Well, it could be the fact that there's a vertical asymptote here. But if I dig in a little bit deeper and back to the top, I actually see that it's going to end up being a hole right there, correct? Because my x minus 2's cancel. So I'll show you what this graph looks like in a minute, but it actually looks something like this, where at 2, there's going to be a hole and it just keeps going. So at A, there is, where's the discontinuity at? It's going to be at 2. And the reason why is because f of 2 is not defined. There's a hole there. Even if you thought there was a vertical asymptote there, it's not defined on a vertical asymptote. So you would still be correct in saying f of 2 is not defined. All right, let's go to B. B, let's see, we have f of x equals 1 over x squared. Let's see, that's going to look something like that. And 1, if x is equal to 0. There's a couple things you could say about this one, all right? You could definitely say that the limit is not equal to the function value. But probably a better answer at this is, look at this. Look what I'm approaching as x gets close to 0. At 0, what happens is this limit is going up to infinity, right? So remember, if the limit's going to infinity, the limit does not exist. So I think a better answer on this is going to be the limit as x approaches 0 of this function simply does not exist. Now part C, look, I get to piggyback off of my part A up here. So what they're going to do on part C is I got this rational function right here, and what they're going to do is they're going to actually fill in the hole, but they're not going to fill it in the right spot. They're going to put it 1 unit down. It looks like it's 1 unit down. It's not at the right spot. Okay. So on this one, again, we have that the limit does exist. We have that at 2, f of 2 is defined. It's taking on this value right here. But what isn't happening is that they're not at the same function mark. All right, one's up here and the other one's down. And so on this one, the limit as x approaches 2 of the function and actually f of 2 just simply are not equal on that one. All right, let's look at D. I think I have a graph of D coming up. And so I'm going to go ahead and just go to the graph of D to kind of show you what's going on. So I just introduced the whole idea of the greatest integer function a while ago. But actually, let me talk about it just a little bit. Because we've talked about this, I think we did 3, like the limit as x approaches 3 of the greatest integer function. I can go ahead and write that. And we said, like, if we approach 3 from the left, then the greatest integer function was 2. Because if we approach 3 from the left, we're looking at like 2.9999999. The greatest integer that is smaller than that is going to be 2. Whereas if I approached 3 from the right, that'd be like 3.000001. I'd be coming in at 3. So I think that this one's not going to exist at 3 because, well, my limit does not exist because my left-hand and right-hand limit are not coming in together. That would be, I think, the best answer on this. But it's more than just 3. What's going to happen at every integer, the limit is not going to exist. So where are the discontinuities? I would just put at every integer. So there's going to be a discontinuity at 0, at 7, at -10, at 100. Every integer you can think of. I did grab some graphs as to what all of these did look like. I already graphed couple of them for you. I really want to show you the greatest integer function. It looks so cool. I just think that is the slickest looking graph right there. And see, where were we at? We were at 3. And there's 2. And there's 3. And there's the reason why the limit from the left and the limit from the right come into 2 totally different numbers right there. So the limit would not exist. Now, just like we have left-hand and right-hand limits, we can also be continuous from the left or the right. Okay? So a function f is continuous from the right at a number a if, make sure I'm in my right spot right here, the limit as x approaches a from the right of f of x is equal to, not L, I'm going to get f out of it, f of a. So we added a little stipulation right there. We're not saying that the limit necessarily has to exist, just the right-hand limit has to exist. So the right-hand limit has to go in to a unique number. It can't oscillate wildly or anything like that. And so you can kind of see what would happen with from the left. The limit as x approaches a from the left of a function is equal to f of a. I still have my 3 things happening. I still have my limit has to exist, my f of a has to exist, and then the limit from whichever side I'm talking about has to equal that function value. Right? So is f of x equal, I'm going back to my greatest integer function. Is it continuous from the right, the left, or both? Okay. Is it continuous from the right, the left, or from both sides? And so to do this, I just need to set up a one-sided limit. All right, I'm just going to do the right side first. I don't know why I do the right side first. It just kind of makes sense to me to do that. And so I'm just going to say x is approaching some number n from the right side of the greatest integer function. Well, just like we saw with 3 a while ago, if I approach 3 from the right side of the greatest integer function, it came into 3. So as long as I'm approaching from the right side, it's equal to n. So I know it's continuous from the right. Because n right here, this would actually equal f of n. I missed that part. So I've shown that the limit as x approaches n from the right is equal to f of n. All right, let's try it from the left. The limit as x approaches n from the left of our greatest integer function. Again, what we saw with the 3, when I approached 3 from the left, it was like 2.99999. We saw that it was actually 1 less than what this n value was, n minus 1, which is not what f of n is. All right, if n right here, coming all the way back right here, if this n is 3, and I'm approaching it from the left, I can expect my value to be 3 minus 1, no matter what integer I'm trying to approach. And so that would have to be, it would go down 1, it would go down to 2. So it's not continuous from the left, it's only continuous from the right. Now we're about to encounter a part of this. It's going to have a lot of definitions, a lot of theorems, and it gets pretty long and can be pretty boring. So that's why we have fun in class, and we name all of our definitions, theorems that go unnamed for the rest of this section. So if you have the unfortunate task of just having to watch this video and we didn't get to name them in class, I apologize, because I'm not sure what we're going to name them from year to year. It changes every year. Now, just like we can be continuous at a number, we can also be continuous on an interval. Right? If I'm continuous on an interval, then all I need to show is that I am continuous at every number on the interval. And so if f is defined only on one side of the endpoint of the interval, then we understand continuous at the endpoint to mean continuous from the right or continuous from the left. Okay? So I'm not wanting to show this as continuous at one point on example 4. I'm wanting to show that it's continuous over this whole closed interval from -1 to 1. And this gets a little bit weird trying to show this. Okay, so I'm telling you that it's going to be continuous. I'm telling you that the limit's going to exist. That it's going to equal f of any number on that interval, and that and that every number on this interval is going to work, I just need you to show me this, kind of like a proof, okay? So first thing I'm going to do is I'm going to set up my parameters. I'm going to set up my parameter A, because we're used to showing it continuous at some number A. A is just going to be just a number that's between -1 and 1, okay? So what's going to happen with that is if I take the limit as x approaches A of something on that function, then that's just going to be the limit as x approaches A of 1 minus the square root of 1 minus x squared. Yeah, this might make sense to you. Yeah, everything's got to be continuous on this interval, but you have to show me. You have to show me step by step how this is going to happen. And so to do that, if I fall back on my limit laws always work. I can take the limit of the difference as the difference of the limits. Okay? Oh, I left off something really important, these equal signs. Don't know how much room I'm gonna need, but if I take the limit as x approaches A of 1, if I take the limit of any constant, it just gives me a constant, 1. Minus, well, the limit of a square root, the limit can actually work its way inside the square root, 1 minus x squared. So now I have 1 minus the square root of, well, I'm going to take the limit into that difference as well. The limit as x approaches A of x squared. I apologize, I don't remember all of my limit law numbers, but again, if I am taking the limit of a constant, I know it's a constant. It was in that second group that we did. And if I'm taking the limit as x approaches A of something raised to a power, I can just plug in that A into that x. So what I have now shown is just, I'm back up to exactly what I had here, except for I've plugged in an A in for that x, which is my exact definition of f of A. So I've shown that f of A is equal to, all the way back to the limit as x approaches A of f of x. Some other things that work for continuity. I'm going to go to erase all opportunity right there. Is if I have f and g are continuous at A and C respectively, continuous at A and C is a constant, then the following functions are also continuous. And it's pretty much just going to be all of my operation of functions. So f plus g is going to be continuous. If I take my two functions and subtract them, whatever function that gives me, that is going to be continuous. If I just take a constant and multiply it by my f, that is still going to be a continuous function. If I take f times g, that is going to be a continuous function. Sorry, it feels like I'm skipping something. And if I take f divided by g, that is going to be a continuous function, given that f divided by g, that function exists. In other words, g of x is not my zero function, or I guess it would be g of A. Also, we have Theorem 5. It says that if I have a polynomial function, it's going to be continuous everywhere. Now, think about your polynomial functions. The domain of a polynomial function is always all real numbers, right? And so there's nowhere for it to break or have a gap or a hole or anything like that. So it's going to be continuous on all real numbers. And a rational function is going to be continuous wherever it is defined. So as long as there's not a hole or a vertical asymptote there, it's going to be continuous at wherever doesn't make the denominator equal to 0. That's another way to say that. So, using that idea, I want to find the limit as x approaches -2 of this function. Okay, I'm looking at this function right here, and sure enough, it is going to be a rational function. If you're not sure why that's a rational function, you're a little bit behind. I'll remind you, it's a rational function is simply a polynomial divided by another polynomial. There's no square roots, there's no funky fractions inside the exponents, there's no crazy exponents. We're good on this. So, according to the theorem 5 that we just had, it's going to be continuous on its domain. Let's talk about its domain real quick. All right. I get -3x cannot equal -5. X cannot equal 5/3. So, theorem 5 stated that as long as I have a rational function, it's going to be continuous on where it's defined. It is going to be defined everywhere except for -5/3. That does not include this -2 right here. So this is a continuous function, meaning that whatever this limit is as x approaches -2 of this whole function is the same as f of -2. So all I got to do is plug in -2 in for all those x's. You might be thinking, this looks a lot like our direct substitution idea. It absolutely is our direct substitution idea. All right, this is why direct substitution works, is because it's a continuous function at this point. And so I got all that to be -1/11 when I plugged that in. If you got something different, let me know. We got some more limits to find here. See, limit as x approaches 0 of sine x. Again, think about sine x. Sine x is a well-behaved function. So I could make a chart. I don't have a cool dividing out technique or multiplying by a reciprocal, anything that will work on this, but it looks a lot like a polynomial. And so I'm willing to bet that this limit's going to exist wherever it is defined, a lot like a polynomial in a rational function. So that means I can just find f of 0, or in this case, which would be sine of 0. Sine of 0 comes out to be 0. And again, that's working because sine is a continuous function. Not only is it a continuous function at 0, it's a continuous function from -infinity to infinity. So I can always plug that in. Same with cosine right here. It's going to be f of, looks like we're approaching 0 again. So I'm able to just take cosine of 0. Cosine of 0 gives me a function value at 1. Now, not all the trig functions work. Tangent has some discontinuities. And tangent's going to have some discontinuities wherever, well, since it's sine over cosine, tangent's going to have some discontinuities wherever cosine theta is equal to 0. Okay. So there's a couple ways you can think of it. Well, where is cosine theta equal to 0 at? Cosine theta equals 0 at all the odd multiples of pi over 2 is what we stated. Or, we are kind of good with working with tangent. We have all these little snakes on a plane, right? And so think about where it's discontinuous at. It's continuous on this whole snake right here. That little snake got away from me a little bit. Where it's discontinuous is in between these snakes. And so what we learned last year was for tangent, all of these snakes were at every odd pi over 2. So where is it discontinuous at? It's plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2. Let me just keep that pattern going. And again, that's where all my vertical asymptotes are, and it's also where all of my cosine thetas are equal to 0. It's all the thetas where cosine's equal to 0. So to say all that, we kind of have a new theorem here. That's going to kind of cover a little bit more than Theorem 5. So I'm going to list out all the types of functions that are continuous at every number in their domain. We already know that polynomials work. And we know that rational functions work. Root functions also work. Trig functions, they're going to be continuous wherever they are defined. Okay. Exponential functions, and logarithmic functions. All of those will work. I put a comma there. I'm actually done with my list. Logarithmic functions. All these functions that we've already talked about, you know, there's some exceptions in there, but a lot of them that we talked about, if they're defined at a number, they're going to be continuous at a number. One group several years ago called this a chandelier theorem. It kind of covered all of our types of functions that we talked about. Okay. So what we're able to do now is we're able to take this complicated algebraic function that we have in example 8, and we can be able to tell where it is going to be continuous. All right. So looking at this one, let's see, I've got a natural log function. Okay, natural log function. Well, when I think of natural log, I know I can't take natural log of anything negative, nor can I take natural log of 0. So this is going to be continuous on, again, its domain from 0 to infinity. 0 is not included on that. Tangent inverse. Well, if tangent inverse is just a snake, the inverse of it is going to be whenever that snake is laying down. It looks a lot like the cube root function. That covers everything from left to right. So tangent inverse of x is going to be continuous everywhere on all real numbers. Okay. So what we have for the top between these two, I'm looking for the overlap. What's in both of these? Well, if this is all real numbers right here, the overlap is just going to be from 0 to infinity. Let's look at the denominator, though. The denominator, I have a nice little polynomial function, x squared minus 1. It's actually a quadratic, and we know that quadratic parabolas are going to have a domain that goes from negative infinity to infinity. But it's in the denominator. I want to make sure I can find out where that denominator is equal to 0. So if I add 1 to both sides and then take the square root, I know my x, I don't want it to equal positive or negative 1. So if I mix this with what I had from my numerator right here, I should get where this is continuous. Okay, so f is continuous on the following interval. Let's see, negative 1 is not even in this, so I don't have to worry about negative 1 at all. But from 0 to 1, that's going to be where it's continuous. I need to skip over 1 and then go from 1 to infinity. Again, it can't be 1 because that makes the bottom equal to 0. There's probably going to be a vertical asymptote there, and there's going to be a gap there. So the left-hand and right-hand limit might not meet up. Something's going to happen. Or I guess that f of 1 is not even going to be defined. More theorems, just like you were hoping for. Uh-oh, we skipped some. Did we skip one? Might not skip one. I don't know. We're just going to evaluate this one. To erase all opportunity. I'll take it up on there. There we go. So I want to evaluate this limit. This kind of came out of nowhere. I thought we was talking about something else. But again, if I want to evaluate this limit, I'm wanting to see if I can use that direct substitution, because that was really easy earlier. So if I'm evaluating this limit as x approaches pi, well, I know that sine is continuous on all real numbers. And cosine will be as well, plus 2. That's just going to move it up 2 units. So that's also going to be continuous on all real numbers, except for the fact that, well, let's see, 2 plus cosine x. I need to find where that's equal to 0 at. Oh, good news. If I subtract 2 from both sides, cosine x can't equal negative 2. Well, that's fine. Cosine x never does equal negative 2. It just sits here and oscillates between positive 1 and negative 1. It never comes down here and touches negative 2. So this down here is also going to be continuous on all real numbers. So yeah, I can take this and I can just do f of pi. So I can just plug pi into these and be set. Sine of pi is 0. Cosine of pi, though, is a negative 1. Everything came out just fine. And so if I evaluate that limit, I do get 0. I believe now I'm ready for more theorems. A lot to take in. Hit pause if you need to. Go get a drink. Take a deep breath. Go for a run. Whatever needs to happen. Theorem 8, again, we'll name Theorem 8 in class. It says that if f is continuous at v, and the limit as x approaches a of g of x is equal to b, then the limit of f of g of x is equal to f of v. Or, in other words, if I'm able to take the limit as x approaches a of a composite function, I'm going to call this of x, I should be good to move that limit on the inside and just do f of the limit as x approaches a of g of x. Sometimes this will help, sometimes it doesn't. Looking at this next problem right here, this all gets pretty messy to deal with arcsine of all this. You know, like I got an opposite here and a hypotenuse. I'm going to have to draw a triangle. That triangle is not going to come out very nice. Or I can use this theorem 8 that's at the top of the page, and I can do arcsine of the limit. This limit can go inside right here. How nice is that? I already got a grouping symbol. No. Oh man, I was so close. What, plugging in 1. It's not in the domain of this function. Or is it? Think I can factor this? I think I can. Top doesn't factor. Does the bottom factor? To you, it might not factor, but I see difference of 2 squares. One's plus, one's minus. I can take the square root of that 1, put it here and here. I can take the square root of that x, put it here and here. And just like that, I've used my dividing out technique. I'm just left with the 1 up here on top. Now I can plug in this 1 and use a direct substitution, because now this 1 is in the domain of this problem. So let's see what I have here. I have arcsine of, let's see, if I plug in 1, I got a 1 on top. And if I plug in a 1 on bottom, I have 1 plus the square root of 1. That's just 1 plus 1 is 2. Arcsine of 1/2. I can evaluate that. It comes out to pi over 6. I'm still counting 2 more theorems. We're getting close. If you're watching that little bar at the bottom, getting close. And I think we're about to prove why the chicken crossed the road. So you definitely want to stay tuned for that. So we got theorem 9 now. If G is continuous at A and F is continuous at G of A, then the composite function f of G is continuous at A. They use continuous a lot. Let me rewrite this in my words. We can simply say a continuous function of a continuous function is a continuous function. So if I'm composing 2 continuous functions, I can expect my answer to be a continuous function. So where are these 2 continuous at? Well, what I'm going to do is I'm going to break this down, okay? So my h of x, let's just suppose my h of x is f of x of g of x. So my g of x function is my inside function, that x squared. Well, this is continuous everywhere. Because if I have just x squared, that's just going to be a parabola. There's no breaks or anything in it. So it's continuous from negative infinity to positive infinity. Okay, let's look at my f function. Well, it's just sine. If you've watched any part of this video, I've already said that sine is going to be continuous on all real numbers. So what does that mean for me? If my h of x up here, this sine of x squared, an equal sign, I'm just stating it, is going to be continuous on all real numbers. Continuous function of a continuous function is a continuous function. Well, let's look at one that maybe handcuffs us a little bit. Okay, my inside function, again, is going to be what's just inside parentheses right there. This 1 plus cosine x. All right, and that's going to be continuous everywhere. And so my f of x is the natural log of x. That one's got a restriction on it. All right, natural log of x is only continuous from what, 0 to infinity? That's pi. It's been a long Monday. I'm ready to go home. So looking at this, that means that this 1 plus cosine x is only going to be, the whole function is only going to be continuous whenever this is able to stay on the positive side. Okay? Which that's going to be true whenever cosine x is able to stay bigger than negative 1. When's cosine x stay bigger than negative 1? It's a great question. Yeah, I'm going to graph myself a little cosine function right here. And so cosine x equals negative 1 at all of these values right here. So where do all those values occur? Well, they happen at pi. So this peak up here is 2 pi. Happens at 3 pi. The next peak would be 4 pi. It would happen again at 5 pi. It happens at negative pi. Happens at every odd pi. So where is that continuous at? I can tell you where it's discontinuous. I guess we could say just everywhere it is continuous, except plus or minus pi, plus or minus 3 pi, plus or minus 5 pi, dot, dot, dot. I'll get the idea that you mean every odd pi after that. All right. Finally. Into this long video, and we get to answer the age-old question of why did the chicken cross the road? Okay. Why did the chicken cross the road? Well, the answer to that is going to be the intermediate value theorem. Intermediate value theorem. Now this one's actually named, so it must be important. If I think it's important, you're probably going to see it on a quiz or a test. But the intermediate value theorem says, suppose that we have f is continuous on a closed interval a to b. I'm going to let n be any number between f of a and f of b, where f of a is not equal to f of b. Then there exists a number c in a b such that f of c equals n. Say what? Okay. This is going to be my road right here. I'll let that run solid line. Okay, so suppose that I have a spot right here at A. Okay, got another spot down here at B. Okay. And so at A right here, we have this little chickadee down here, and the little chickadee's just taking it's just merry time to cross the street. Okay. Now, what happened though is at point A over here, the chickie was over here or down below the road, and point B, the chickie is above the road. So, since the chicken's path right here is a continuous function, there's no breaks there, there's no holes, there's no jumps, there's no nothing. At some point between A and B, there has to be a point C. I'm just going to say the chicken had to actually cross the road. There's some point C right here where the chicken crossed the road that is of interest. Okay? And where that chickie crossed the road at, well, this is going to be my f of A. Just happen to be right there on my axis. Right here, this point coming back is going to be f of b. This point of interest right here is going to be my n, which has to be between f of a and f of b because we had a continuous function. Okay? And the whole idea is this n is going to map up exactly where f of c is equal to. So, someone says, why did chicken cross the road? Tell them the intermediate value theorem. It's the same slide here. How are we going to use this? This is going to be one of the first things that we use in our, we're going to use this with the mean value theorem and, I can't remember the guy's name, I think it's Fermat's theorem. And we're going to be able to take this a lot further later on. But right now I'm just wanting to look at this primarily just algebraically. And I'm just wanting to show that there is a root in this equation right here. And the root's between 1 and 2. Okay, so just going back to our chicken. Alright, so here's 1 on the road, here's 2 on the road. And so evidently, somewhere between 1 and 2, the chicken's going to cross the road. And I just want to prove that mathematically. Okay. Now, in order for it to be a root, all we're saying is that there's going to be some value of x that makes this function equal to 0. Okay, so if it's between 1 and 2, what I can show first is I can find f of 1. Like I said, this is going to be very algebraic right here. Not much calculus to do with this. You can actually find this in most algebra books. So what I did was I plugged in 1. I'm going to find that function value. It's at -1. That kind of makes sense. The chicken right here is on the negative side of the road to start with. Okay. Now, I'm gonna hopefully hope that he's on the positive side of the road right there at 2. If I'm not plugging in something right, I apologize. I'm just going off my notes here. But when I plugged in 2, I got it to be 12. So yeah, the little chicken definitely made it to the positive side of the road right here. And so what we've shown is that 0 is in between f of 1 and f of 2. And so this number right here, wherever it happens to fall, is going to be my n that landed between 1 and 12. And I'm just wanting to show that that n right there was 0. And so to wrap this up, I'm wanting to show, I'm telling you that there is going to be a root right there. And so this shows it. By getting a negative and a positive number, I can wrap this up and I can say by the intermediate value theorem, and I just call it IVT, there is a C such that f of C equals 0 because let's just start that word all over, because, not much better, but a little bit, f is a continuous polynomial. Therefore, f of x has one root. We're going to call that one root c. We're not even worried about finding what it is on the open interval from 1 to 2. But this is going to be the c right there. That landed right between it. Okay. That's really all I have. I did want to show you, though, that what this actually does look like if I was to actually use this correct equation. Okay. So I'm going to pull up my graph. Oh, the sun's really coming in on that. Oh man. Let me grab a folder real quick. Let's shield that. You see that? All right, that's better. Okay, so what I've done is I've went ahead and put in that function. Okay, and just a simple graph is going to show what it's going to do. Hopefully, we're going to see it come up from the bottom. And yeah, that blue line right there is supposed to mimic the chicken's path. And as you can see, it is crossing the road, or the x-axis, right there between 1 and 2. And so I feel good about my conclusion. All right, that is the problems. I'm going to focus your quiz after. Sorry, you can't see them. My board, just pull that down. And so I have questions on this ready for me. Good luck. All right. I think you should have some really good questions for me, and I look forward to answering them. Until next time, guys, be good, stay safe. Catch you then.